Can every continuous function be obtained as the derivative of another function? And if so, how exactly do we construct it? To answer that, we turn to Walter Rudin's Principles of Mathematical Analysis. This text provides the rigorous machinery necessary to bridge the gap between differentiation and integration in higher dimensions. Our focus is located here in Chapter 10. Under the section Integration of Differential Forms, Rudin introduces a specific tool, the primitive mapping. In standard one-dimensional calculus, a primitive is simply an antiderivative. It serves a clear geometric purpose, calculating the area under a curve. But Chapter 10 transitions into n-dimensional space, where the definitions require more precision. In multivariable analysis, a primitive mapping is a topological transformation. It is defined by its action on the coordinate axes of a set. While one-dimensional primitives find areas, multivariable primitive mappings allow us to break down complex multidimensional volume problems into manageable one-dimensional components. Conceptually, this mapping is a spatial transformation that alters one and only one coordinate axis. Look at the formal definition. Mapping G acts on an open set E. For all indices not equal to m, the coordinates remain unchanged and locked in place. Only the mth coordinate is transformed, governed by a function called alpha of x. Geometrically, the mapping pushes space along a single directional rail, while the rest of the coordinate system remains rigid. This behavior enables the proof of the general change of variables theorem for multidimensional integrals. These primitive mappings are the indivisible atoms of topology. Chained together, they can construct any complex spatial distortion. To use this topological atom for integration, we must calculate its multivariable derivative. This requires the Jacobian matrix for mapping G. Because other coordinates are rigid, the matrix fills with ones along the diagonal and zeros elsewhere. We populate the blank mth row with the partial derivatives of alpha of x for each spatial variable. This structure simplifies the calculation of the Jacobian determinant. The determinant of this entire matrix collapses entirely to a single value, the partial derivative dm of alpha of x. This result bridges the gap back to standard one-dimensional calculus principles. Rudin leverages this simple determinant in the factorization theorem, found on pages 248 through 251. This theorem applies to any mapping F that is continuously differentiable and has an invertible derivative. For these mappings, the multivariable derivative can be factored into a sequence of simple one-directional determinant calculations. The factorization theorem allows us to view a complex simultaneous spatial distortion as a composition of simpler moves. We can break a single complex move into steps, stretching first horizontally and then vertically to reach the exact same final shape. This is why the derivative of f must be invertible. Without invertibility, the transformation collapses dimensions entirely, making it impossible to define the sequence. Differentiability provides the mechanism to untangle these nonlinear spatial mappings without tearing the topology. Step 1 of the proof: permute the spatial coordinates so that the top left n-1 submatrix of the Jacobian is invertible. Step 2. Define a mapping G that leaves the first n-1 coordinates fixed, but applies mapping F's last coordinate. By this definition, our constructed mapping G is a primitive mapping. The inverse function theorem from Chapter 9 guarantees that G is locally invertible. Step 3. Define a composition H as F composed with the inverse of G. This construction neutralizes the nth coordinate. Consequently, the mapping H leaves the nth coordinate completely unchanged. The mapping H now only acts on n-1 dimensions. We can now apply this entire factorization process again to the mapping H. This process continues, stripping away dimensions one by one until the mapping is entirely factored into primitives. Rudin achieves this result through systematic finite dimension reduction. How does breaking a mapping into these topological atoms solve integrals? Compare these two side by side. On the left, the fundamental theorem of calculus. On the right, the multivariable change of variables. The fundamental theorem links one-dimensional derivatives to area. Similarly, the change of variables links the multivariable Jacobian determinant to volume scaling. Because the Jacobian determinant of a primitive mapping collapses to a single partial derivative, calculating its volume scaling is a trivial step. Integrating over a complex region is equivalent to integrating over a sequence of these simple deformations. Rudin's primitive mapping translates the chaotic geometry of n-dimensional space into the territory of single-variable calculus. First, recall that a primitive mapping in n-dimensional space alters just one coordinate axis at a time. Second, any smooth, invertible space transformation can be built from a sequence of these primitive mappings. For exams like the CSIR net or gate, remember that Rudin's topological primitive mapping is distinct from finding a one-dimensional integral primitive. Like, subscribe, and click the bell icon for more chapter-by-chapter explanations of Walter Rudin's Principles of Mathematical Analysis and other advanced mathematics texts.